All right, so we're back on section 4.4. This is the second part of that section. So after you complete the second piece, you should be able to do your homework, the 4.4b assignment. All right, so what we talked about last time in 4.4a is how to solve things when we can write both sides with the same exponential base, which we can just drop them, right? Or if we can write both sides with the same log base, then we can drop those log base. What we're going to look at today is solving log equations or exponential equations where not all the terms have the same exponential base, or not all the terms can be written as the same log base. Maybe not even all the terms have a log in them. All right, so for exponentials and for logs, we kind of have different goals. For exponentials, our goal is to either use the common log or the natural log and rules of logs to change forms. Now, if both sides are not written with the same number, then we're probably not going to pick one or the other and use log base that number, because then we're going to have to do change of base later. So we're pretty much going to stick to common log or natural log because we have those buttons already on our calculator and it just makes life a little bit easier. Okay. Now when we're dealing with logs, we want to make sure that all our log terms are on one side and isolated, and we want to make sure that we condense them into one. Okay. And then whatever terms don't have a log, we want them on the other side. And once we get one log term is equal to just a number, then we can change forms to solve. Okay, so I'm going to go ahead and show you what we're looking at. So we're first going to look at exponentials. Okay, so with exponentials, notice there's no way I could write this 10 and this 2001 with the same base. I can't write 2001 as 10 to some power. So I'm going to pick either the common log or the natural log to simplify this. Because this is a 10, I'm just going to use common log because common log is base 10. So I'm going to do log of 10 to the x minus 9 is equal to log of 2001. So this is helpful because my log and my 10 are going to cancel because this is log base 10 and log base 10 of 10. They're inverses, so they cancel out, and I'm left with x minus 9 equals log of 2001. Okay. Now, this log of 2001, that's something we can do on our calculator, and I'm going to punch that in here in just a second to see what that equals. On the other side, I'm going to go ahead and move this 9 over. Now, when I move this 9 over, I can't combine it with this 2001 because that's stuck inside the log. So don't make that mistake. So we have x is equal to log of 2001 plus 9. And then we're going to go ahead and punch in log of 2001 in our calculator, which comes out to approximately 3.30124 and a bunch of other stuff. Now, if you can keep at least 5 decimal places, your answer is probably going to be correct, but I highly suggest leaving all your decimal places if possible. Okay, plus 9. So when we add 9 to that number, we get 12.30124 and some more stuff. And then notice up here at the top, it said round your answer to the nearest hundredth. When we talk about the nearest hundredth, that means 2 decimal places. So if I go to the second decimal place here, it's a 0. Notice there's a 1 behind it. The 1 behind it isn't going to bump it up. So I end up with x is equal to 12.3. Now, because this was an exponential, I don't have to check my answer. That's my solution and I'm good to go. Let's look at another one. On this one, I have 2 times e to the 3x equals 145. Now, my exponential, there's no parentheses around this 2 and this e. So e is the only thing with an exponent. So I'm going to get rid of this 2 because it's not tied to that. So I'm going to divide both sides by 2, which gives me e to the 3x is equal to 145 divided by 2. I'm going to go ahead and just give a decimal answer since I know I get to round my answer. And this is 72.5. Okay. And now again, I want to use either the common log or the natural log. Since this is exponential base e, I'm going to use the common log because I know the common log is log base e, and that way those will cancel out. So log base e of 3 to the x is equal to ln of 72.5. Okay, my ln and my e will cancel because they're inverses, which leaves me with 3x is equal to ln of 72.5. Now again, this ln of 72.5 is something I'm going to do in my calculator in just a minute, but I'm going to go ahead and isolate x by getting rid of that 3 by dividing. Now another big mistake, people will try to do 72.5 divided by 3 and then take the ln. Don't do that. The ln and the 72.5 are stuck together like glue. So do that as one piece and then divide by 3. When I plug in ln of 72.5, that gives me 4.2835 and some more stuff. And then when I divide it by 3, I end up with 1.4278 and some more stuff. And then again, we're rounding our answer to the nearest hundredth. So the nearest hundredth here is the place that has the 2 in it. Because there's a 7 behind it, I'm going to go ahead and round this up to 1.43. Again, because we're dealing with exponentials, I don't have to check my solution. I can just leave it like that. Okay. Let's look at one that's a little bit nastier. Okay. Now that we have the hang of it. Okay. Now this one, our unknown is still stuck in an exponent, but notice this exponent is on this super nasty term, right? So what I need to do is first of all get this super nasty term isolated. So I'm going to go ahead and divide both sides by 3,500. So if I can divide both sides by 3,500, that gets this thing by itself. So 7,000 divided by 3,500 gives me 2 is equal to 1 plus 0.027 over 365 raised to the 365t. Now, I need to be able to get this gone. Now, I don't really know what this equals off the top of my head, but to get rid of this ugly base, I don't want to have to do log base ugly to get rid of it. So I'm going to use just a regular old common log. You can also use natural log. I'm going to use common log just because that's what I usually pick. And I'm going to take log of both sides. So I have log of 2 is equal to log of 1 plus 0.027 divided by 365 raised to the 365t. And the reason I'm doing that, even though it may not look like I'm making it better, my ultimate goal is to solve for t. And t right now is stuck to this 365 that's up in the exponent. So by taking the log, I can now use that property that says if I have an exponent, I can pull it out front as a coefficient. So I'm going to pull this down in front, so I have 365t times log of that nasty. Log of, and I'm going to go ahead and calculate this in my calculator. I think, again, if you know how to use the memory button on your calculator, that would be a good method to use so that you keep as many decimal places as possible. So if I do 0.027 divided by 365 and then add 1 to it, I'm looking at 1.00007397 and some more stuff is equal to log 2. Okay. So again, I'm still trying to get this t by itself. So what I'm going to do is I'm going to slowly get t by itself by first dividing off this nasty log that I no longer need. So I'm going to divide by log of 1.00007397 ... And if I divide by that on this side, I have to divide by it on this side. Log of 1.000073 ... Okay. So once that cancels, notice what I'm left with is now I just have 365t on one side, and on the other side, when I simplify this mess, log 2 divided by log of that nasty number, I should be left with, actually I'm going to go ahead and write out what those two equal, just so that you can check yourself if you're working this on your own calculator. Log of 2 should give us 0.30 102 and some more stuff. And when you do log of this nasty number, now when you're calculating this in your calculator, you probably want to go back up here where you have 0.027, divide that by 365, add 1 to it, and then take the log of that so that you have all the decimal places of this nasty number. Okay, and that should give you 3.2124 blah blah blah. Okay, so I have 365t is equal to, when I divide these two numbers, it should give me 9,370.669 and some more stuff. Okay, so this is looking better. I know it seems horrible, but we're just trying to whittle down to solve for t. So notice the only thing I have left to get rid of is this 365. So I'm going to go ahead and divide off that 365, which will give me t is equal to 25.6730 and some more stuff. And again, we're still rounding to the nearest hundredth, so that's the second decimal place, which is my 7 here. And the 3 behind it is not going to move that up. It's not going to bump it up. So I end up with t is equal to 25.67. And I can leave it like that. Woo, right? So this is what I'm talking about. Instead of doing, when we got to this point right here, let me get a bigger dot so you can see what I'm pointing at. When we got to this point right here, we could have taken log base 2 and tried to get rid of this, or we could have done log base 1.00079, but that would have made us have to do change of base later, and that's not fun. So by using just a regular log on both sides, as long as we have a log, then we can take that thing that's in the exponent and bring it down out front as a coefficient, okay, which is what we did here. Then once we brought that down, then we can just divide off the pieces we don't want. It just so happens the pieces we don't want here were kind of ugly, but that's okay. We can handle it, right? Let's look at a couple more examples, and then I'll have y'all try some. All right, so on this one, notice it's good. We have an E. Anytime I see an E, I'm going to use the natural log, because by using the natural log, it'll make that E cancel out, and that's one less nasty piece we have to deal with. So notice there's nothing I can do to write E in terms of base 8, right? And I can't write 8 with an E to some power. So I'm going to go ahead and just take the natural log of both sides. So natural log of E to the negative C is equal to the natural log of 8 to the 2c. On this side, my natural log and my e are inverses, so they cancel, which leaves me with negative c is equal to the ln of 8 to the 2c. Now, I'm solving for c, and right now this one is stuck in this exponent. So we can do this one like we did the last one and take this down as a coefficient. Okay, so that's what we're going to do, so that we'll have 2c out front. So I have negative c is equal to the 2c that we brought down times ln 8. Okay, and now if I want to solve for c, this is pretty easy. I need to get all my c terms together, right? So I'm going to move this negative c over to this side. So I'm going to add c to both sides. So I have 0 is equal to 2c ln 8 plus c. Now again, we're solving for c. I have a c stuck in this term, and I have a c stuck in that term. So in order to get my c by itself, I'm just going to factor it out. If I factor the c out of this term, I'm left with 2 ln 8. And if I factor the c out of this term, I'm left with just a 1. Okay. And then once we get it solved, I just set each of these equal to 0 and solve. Notice this is just a constant term. So this doesn't have any c's in it. So even if I set that equal to 0, it's not going to equal 0 because it's just a constant term. So I'm just going to set the c equal to 0, which is my solution. C equals 0. So all that work, I didn't necessarily have to do it, right? Or I will say it this way. What I could do, if you want to think about it, because some people are bothered by this just not mattering, this is all just one big number. So you can think of it as a coefficient. So we could go ahead and divide off 2 ln 8 from both sides, okay, plus 1. If I divide off 2 ln 8 plus 1 off of both sides, it cancels on this side, and on the other side, 0 divided by a number is still just 0. So I end up with C is equal to 0. Okay? All right, let's look at another one. On this side, notice I have a 2 as my exponential base on the left and a 5 as my exponential base on the right. Those cannot be written in terms of the other one. I can't write 2 with an exponential base 5. I can't write 5 with an exponential base 2. So I'm going to use just a regular old common log, and I'm going to take log of 2 to the 5th is equal to log of 5 to the 4 over x. And the reason I'm doing this is so that I can take this unknown value that's stuck right now in the exponent and bring it down in front. I can only do that if I have a log term, and I can only put a log term there as long as I put a log term on both sides. So now on this side, this is something that I can calculate in my calculator. So we're going to do that here in just a minute. In fact, it might even be easier . I'm going to go ahead and just bring this 5 down as well, because then I just don't have to deal with any exponents. So I have 5 times log 2, 5 times log 2 is equal to 4 over x times log 5. Now, this x obviously came down from being in the exponent, so that's good, but notice it's still stuck in the denominator, which still doesn't help me solve for it. So I'm going to go ahead and multiply both sides by x. If I multiply on the left side by x, I now just have x times 5 log 2. Or sorry, 5x times log 2. But I'm going to leave it in parentheses because I want that x to be by itself. Log 2. And on this side, my x's are going to cancel, which leaves me with 4 log 5. Okay. So notice I went ahead and left this x outside the quantity instead of writing that as 5x log 2 because I want to get x by itself. And right now, all I have to do in order to get it by itself is divide off this 5 log 2. So I'm going to divide both sides by 5 log 2. So I have x is equal to, now this again is something you want to do in your calculator. If you don't have a calculator that can store numbers, make sure you leave at least 5 to 6 decimal places so that your answer is accurate. Okay, I'm going to go ahead and write what each piece should equal so that you can check yourself as you go. 4 times log 5 should give us 2.79588 and some more stuff. On bottom, 5 log 2 should give us 1.505149 and some more stuff. So when I divide these two numbers, either using my calculator with parentheses or if you're using your memory, doing your memory recall, you end up with 1.8575 and some more stuff. And just like all the other problems, I'm going to go ahead and round to the nearest hundredth, which is the second decimal place, which is my 5 here. Notice because I have a 7 behind that 5, that's going to bump it up. So I get x is approximately 1.86. I leave it like that. Okay. All right, I'm going to do one more, and then I'm going to put some up for you to try. Okay. All right, so on this one, notice 4 can't be written as base 7, 7 can't be written as base 4, so we're just going to use our common log. So I'm going to take log of 4 to the 7x minus 2 is equal to log 7 to the x. Now, The reason I'm doing this, the reason I need a log, is so that I can take this exponent and bring it down as a coefficient. And I want to do the same thing on this side because I have unknowns in both exponents. Now on this left-hand side, when I bring this value down, because I have more than one term, I want to make sure I write it with parentheses. So I have 7x minus 2 times log 4 is equal to the x that I brought down on the right-hand side times log 7. Okay. Now, I want to solve for x. Right now I have this x over here on the right, and I have this x that's stuck in this quantity. So I'm going to go ahead and distribute that log 4 in so that I can get that x term by itself. So what I'm ending up with is 7x times log 4 minus 2 times log 4 is equal to x log 7. So you can see where my two x terms are. I have this x term and I have this x term. So I need to get them on the same side. So I'm going to go ahead and subtract my 7x log 4 term to the other side. So subtract 7x log 4. These logs are not like terms, so I cannot combine them. So I end up with negative 2 log 4 is equal to x log 7 minus 7x log 4. Whoo, right? Okay, so this is good because notice now we have our x terms on the same side. Once we have our x terms on the same side, then we can go ahead and take that x out of both terms. So I'm going to take the x out, which is going to leave me with log 7 from the first term minus 7 log 4. So just factoring out that x equals negative 2 log 4. And now that I have x outside of that quantity by itself, then I can divide off this piece that I don't need. So log 7 minus 7 log 4 divided by log 7 minus 7 log 4. So that cancels, and so what I'm left with now is x is equal to this mess. So this top piece, negative 2 log 4, is equal to negative 1.2041 and some more stuff. On bottom, when I do log 7, that gives me 0.845 and some more stuff minus log 4 minus log 7 minus 7 log 4, which is 4.214 and some more stuff. Okay, so I'm going to go ahead and subtract those numbers on bottom. So on top I still have negative 1.2041 and some more stuff. And on bottom, when I subtract these two numbers, I get negative 3.369 and some more stuff. So again, dividing these out, I end up with 0.3573, and it keeps going. And then I look at my nearest hundredth. Okay, so my hundredths place is the 5. Since there's a 7 behind it, it's going to bump it up. So I end up with x is equal to 0.36. Okay, again, because I don't have a log term, these are exponentials, I don't have to check my answer. So there's 2 for y'all to try. Go ahead and pause the video and work on the practice problems 1 and 2, and I'll put them up here in just a second to go over. All right, so this first practice problem, we need to isolate the exponential. So we're going to go ahead and divide off this 3,500. So we have 2 is equal to e to the 10r. And then because we have a base e, here obviously instead of using the common log, we want to use the natural log because we know the natural log and e will cancel. So we take the natural log of both sides, our e and our natural log cancel, which leaves us with just a 10r on the right-hand side. And then we can get r by itself by dividing by 10. Okay, and I've written here when we do ln of 2 what that should equal. when we divide by 10, what that gives us, and then when we round to the nearest hundredth, okay, always pay attention to your instructions because a lot of times people will miss problems, not because they don't know how to do them, but because they didn't round correctly. So that's 2 decimal places, which means that R is equal to 0.07. Okay, let's look at the second one. Second one's a little bit more difficult. This one, we have 2 bases that cannot be written, obviously, with the same base. And we have unknowns in our exponents. So we're going to go ahead and take either log or ln. Now, if you took log, that's okay. I did ln just so that I could show one where I took ln. So I'm going to go ahead and take the natural log of both sides so that I can bring down this x, and so I can bring down this 2x minus 1. Now, when I bring that down, notice I have 2 terms, so make sure you use parentheses, because now I'm going to distribute this log 3 to both of those terms. So on the right-hand side, I have 2x log 3 minus 1 log 3. Okay. Now remember, the ultimate goal is to solve for x. So since the term on the left and the first term on the right both have x's, I want to move this first term on the right over to the left so that I can combine and get my x's on the same side. So that will make them cancel. On the left-hand side, I now have 2 terms that have x's in them. Okay. To get the x's out of the 2 terms, I factor it out as if it's a greatest common factor. Once I factor that x out, that leaves me with ln 7 minus 2 ln 3. And then to get x by itself, I'm just going to divide off that huge quantity that I don't need. So I'm going to divide by ugly on this side. If I divide by ugly on this side, I have to divide by ugly on this side, right? So I end up with x is equal to negative ln 3 all over ln 7 minus 2 ln 3. And then I simplified the top and the bottom separately so that I can go ahead and divide them, which gives me 4.37 and some more stuff. Round to the nearest hundredth, which leaves me with 4.37. Okay. Again, if you need to look over these or spend more time on them, feel free to pause the video and go through it a little bit slower. Okay. But I am going to go ahead and move on and now look at some with log terms. So we've seen what to do when we have exponentials that don't have the same base. We use either log or natural log so that we can bring down those exponents. Okay. But if we have log terms, we're going to try to change forms to be able to get our unknown out of the log. So let's go ahead and look at this. Now remember, when we're solving for logs, if we have more than one term, we need to condense those terms into one. We need just one isolated log term on one side and then our constant number or value on the other side. We also have to remember that anytime we have logs, we have to worry about log of a negative and log of 0. So we have to check our answers when we're dealing with logs. Okay, so let me go ahead and show you a couple. Let's scroll down here. This one, notice I just have one log term, but right now it's not as isolated as I would like because it has this 3 stuck to the front of it. And I can't change forms when I have a coefficient. So there's 2 ways to get rid of this. I could take this 3 and I could move it up here into the exponent. But what that's going to do is that's going to give me a quantity that I'm going to have to multiply out a whole bunch of times, which is a lot of extra work that I really don't want to have to do. So instead of moving it into the exponent, I'm actually going to just divide it off. I'm going to divide both sides by 3. So I have log base 2 of x minus 1 is equal to 2. And now this is something that I can hopefully change forms. Because I don't have a log base 2 on this side. If I had a log base 2 on this side, I could just drop them like we did in the last video. But since I don't have a log base 2 on both sides, I can't drop them. What I am going to do is I'm going to get rid of log base 2 by using the exponential base 2. So I'm just going to write a big exponential base 2 here and move my whole equation up into the exponent. The reason I'm doing that is because exponential base 2 and log base 2 will cancel. That's going to leave me with x minus 1 on this side and 2 squared on the other side. Now this is something that's super simple and easy to solve. So I have x minus 1 equals 4, and then I move my 1 over, which gives me x equals 5. Then before I can circle it, remember I have to check my answer. So I'm going to go ahead and say check. I'm going to write out my inside value of my log, which is x minus 1, and I'm checking x equals 5. If I plug 5 into this quantity, 5 minus 1 is 4, which is not negative and not 0. So that solution is okay. Okay, let's look at another one. Same idea here. Notice here the log base 7 is already isolated. There's no coefficient. So again, to get rid of log base 7, I'm going to use a big exponential base 7. I can't just drop that log base 7 because there's not one on the right-hand side. But once I write my exponential base 7 on both sides, then I can drop my 7 and my log base 7 on the left because they're inverses. So I get negative x is equal to 7 squared. We know 7 squared is 49. And then to get x by itself, I can just divide both sides by a negative 1. So x equals negative 41. Because I'm dealing with logs that have inside values, I have to check. So I'm going to go ahead and check my solution. I check my solution in my inside value, which is negative x. And I'm checking x equals negative 49. If I plug negative 49 into negative x, I'm going to get double negatives. And then double negatives make it positive. So this actually works out even though it was negative. Okay? All right. Let's look at some more challenging ones, possibly. I'm going to do about 3, and then I'm going to give y'all some to do. So let me go ahead and scroll down. All right. Looking at this one, it's good. We don't have anything out front that we have to get rid of, and we just have one log term. So I'm going to go ahead and figure out how to get rid of this log base 16. Because I don't have a log base 16 on the left side that I can just drop, I'm going to change forms using an exponential base 16. So I'm going to do 16, and I'm going to raise my equation up into the exponent. If I do that on the left-hand side, I have to do that on the right-hand side. So negative 3/4 becomes the exponent on my 16. On the left-hand side, my 16 and my log base 16 cancel. So I have x is equal to 16 to the negative 3/4. Now, I don't like to deal with negative exponents. There's not a whole lot we can do with them negative. So I need to change this to a positive exponent. And remember, the way to get rid of a negative exponent is to move that base across the fraction line. So this is the same as saying x is equal to 1 over 16 to the positive 3/4. When I move that base across the fraction line, the exponent sign changes. Okay? And then I just want to refresh you in case you've forgotten that when we have a rational exponent, this represents power over root. So we have 16 to the 3rd power, and we're taking the 4th root of it. Or we can do it in the opposite order. We can take the 4th root and then raise it to the 3rd power. And that's the way I'm going to do it because I think that might be a little bit easier. If I do the 4th root of 16 and then I want to cube it. So I want to know what number times itself 4 times equals 16. If you know right off the bat, that's great. If you're not sure, you can always factor 16. 16 is 4 times 4, and each of these 4s is 2 times 2. So notice I have 4 copies of a 2, which means that the 4th root of 16 is 2. So I end up with 1 over 2 cubed. And 1 over 2 cubed is 1/8. And then again, because this is inside a log, I need to check that log value. I'm going to go ahead and check. My inside number is x. If I'm checking x equals 1/8, if I plug 1/8 in for x, it's going to stay positive. So 1/8 is my solution. Okay? Let's look at another one. On this next one, I have 2 ways of solving it. The first way is I could solve it exactly like we did the last one. I can see that there's not a log base 3 on this side to cancel, so I can use a big 3 on both sides to cancel that log 3 off. That would leave me with 9 to the 2x is equal to 3 to the negative 2. Now this kind of didn't help me, right? Because even though I got rid of the log, my unknown is still stuck in an exponent. The good news, though, is that both sides of this equation can be written with an exponential base of 3. So I'm going to rewrite this 9 as 3 squared raised to the 2x equals 3 to the negative 2. And then I can go ahead and multiply these exponents on the left-hand side. So I have 3 to the 4x is equal to 3 to the negative 2. And now that I have the same exponential base on both sides, I can just drop those. So when I drop them, I'm left with 4x is equal to negative 2. And then I divide off my 4, which gives me x is equal to negative 1/2. Okay. Now notice my x is coming from the exponent inside here. And exponents can be positive, negative, or 0. Even though it's inside the log, it's not the value inside the log, it's an exponent. So I actually don't have to check my answer here. Okay, so that's one way of doing this, but I actually want to show you the other way. Some of you may have noticed it. Instead of doing this, get rid of the log base 3 by using a big exponential base 3, I'm going to start with the same problem. I could notice that right here, I could get rid of log base 3 because 9 can be written with an exponential base 3. So if I write this 9 as 3 squared raised to the 2x, and I write that as base 3 first, then I'll be able to cancel my log. I can write this as log base 3 of 3 to the 4x, and then my log base 3 and 3 will cancel, which leaves me with 4x equals negative 2. So it's a little bit shorter, but again, either way, notice once I divide off my 4, you'll get the same answer. So just because you're not working it the same way as me necessarily, or the same way as someone else in the class, doesn't mean you're doing it incorrectly, because some of them have several ways that you can work them. All right. All right, let me look at one more and then I'll have y'all try some. All right, so this one is a natural log. Remember, I'm just going to put over here, recall, the ln of x is the same thing as log base e of x. So if I want to get rid of a natural log that's base e, I need to use an exponential base e. So I'm going to use e raised to the ln of x plus 1 is equal to e raised to the 3rd power. So I'm moving that equation up into the exponent so that I can get rid of that left-hand side. So e and ln are going to cancel, which gives me x plus 1 equals e to the 3rd power. And then I need to move my 1 to the other side. So I end up with x is equal to e cubed minus 1. Now e cubed you should be able to do on your calculator. Most of you will have an e button and then like a caret button. Some of you may even have an e to the x button, something of that sort. So when I do e cubed on my calculator, I end up with 20.085 and some more stuff minus 1 is going to give me 19.085 and some more stuff. And then I'm going to round it to the nearest hundredth, which again is that second decimal place. So I end up with x is equal to 19.09. Whoops, I can't circle it yet. You almost let me get away with it. I can't circle it because I haven't checked my solution. I do have to check because this is inside a log value. Okay, so I'm going to go ahead and write over here. I'm going to check x plus 1, and I'm checking 19.09 as my solution. If I plug that in and add 1 to it, I'm going to get 20.09, which is neither negative nor 0. So we're good. Okay. All right, so there are 4 for you to try. So go ahead and pause the video and give those a try. And then go ahead and play the video and we'll go over them. All right, so on this first practice problem, we are going to go ahead and get rid of that log base 9 because we don't have a log base 9 on the other side that we could just drop. So we get rid of log base 9 by using exponential base 9 on both sides. So our 9 and our log base 9 cancel, leaving us with just 2x minus 1 on the left. and then 9 squared on the other side, which is 81. So once we move our 1 over and divide off the 2, we end up with 41. We check to make sure if we plug 41 back into our inside number over here, it remains positive, which it does. Okay. Let's look at the second one. For the second one, we have log of x to the 10th equals 10. Now to get rid of this log, notice there's no number written down here, no subscript. So when there's no number there, it's an implied log base 10. So to get rid of log base 10, we're going to use exponential base 10. If we use a big exponential base 10 on this side, we have to put a big exponential base 10 on the other. So our 10 and our log cancel, leaving us with x to the 10th. On the other side, I have 10 to the 10th. Now I could work this out and see if I could do something, but I noticed this is the same rule we have. You know how we have the same exponential base? We can drop the bases and set the exponents equal. The same thing is true if the exponents are equal. We can drop the exponents and just solve the bases. So notice here, because x to the 10th equals 10 to the 10th, well, the only way that would be true is if x is equal to 10. So we can just drop these 10s in the exponent and say x equals 10. Once we get x equals 10, because this was inside a log, we do have to check our solution. Luckily for us, it checks out. So x equals 10. Let's look at number 3. Number 3, we first have to isolate the log by dividing off that 5. When I divide off that 5, I get log base 4 of x plus 6 equals 2. Now I don't have a log base 4 on this side that I can cancel, so I have to use exponential base 4. When I put exponential base 4 here, I can cancel it out on the left. Exponential base 4 on the other side just leaves me with a 4 squared, which is 16. So then I can go ahead and subtract my 6 across and get 10. Notice when I check it with my inside value, it checks out and I get 10. Let's look at one more. For this one, we have natural log of 2x equals -1. To get rid of a natural log, that's a log base e. So I'm going to use exponential base e. I use exponential base e on the left to cancel that. Whatever I do on the left, got to do on the right. So I get e to the -1 on the right-hand side. Then all I have to do is divide off that 2 to get x by itself. And then I went ahead and put what it equals in the calculator here. E to the -1 should give you 0.36 and some more stuff. When we divide it by 2, we get 0.1839, and then we round it to the nearest hundredth, which gives us x is 0.018. When we check it in our inside number, everything checks out, so we're good. All right, so we've gone over how to solve exponentials when they don't have the same base or they can't be written with the same base. And now we've just talked about how to solve logs when we don't have logs on both sides. We're going to look at the same idea as these ones we just did. The only difference is we might have more than one log term. When we have more than one log term, before we get started canceling out logs, we have to make sure that we condense everything down to just one log term, and then we can do the same process we were doing. All right, so let's look at one. Again, notice here it's saying round our answers to the nearest hundredth. On my math lab, make sure you pay attention. It might say to the nearest whole number, to the nearest 4 decimal places. Okay, for our notes, we're just going to do the hundredth. All right, so here we have log terms on one side and a constant on the other. So I know I'm not going to be able to drop these log terms because I don't have one on this side. So I'm going to go ahead and just condense these. I'm going to condense using division because these are being subtracted. So I'm going to write this as one natural log term, and the one that's being subtracted, remember, goes on the bottom. So 4 goes on top over x equals 0. Okay. All right, so now that it's condensed into just one log term, now I can get rid of this natural log. To get rid of this natural log, I need to use the base of a natural log, which is e. So I'm going to use big exponential base e on both sides. That way it will cancel on the left, and we'll be left with 4 over x is equal to e to the 0 power. Now anything to the 0 power equals 1. So I have 4 over x equals 1. And then to get x by itself, I'm just going to multiply both sides by x. That way it will cancel over here on the left-hand side, and I'll be left with 4 equals x. So that gives me my answer. Because it was inside a log, I do have to check my solution. My inside values here were 4 and x. So if I check x equals 4, obviously the 4 is going to stay the same, and the x is going to be 4. So either way, we have no problems. Okay, not too bad. So condense and do the same problem. So let's look, sorry, the same process. So let's look at this next one. Same idea. I don't have log. Every single term is not a log term. So I'm not going to be able to just drop my logs. So I'm going to condense and then use the exponential base to get rid of the log. So when I condense these, because it's an addition, it condenses into multiplication. So I'm going to write this as log of x minus 2 times log of x plus 2. Okay, so I've got it condensed. I have it looking the way I want, but now I need to get rid of this log term. Notice there's no subscript, so it's an implied 10 as my base here. So to get rid of log base 10, I'm going to use exponential base 10. So those will cancel on the left, leaving me with x minus 2 times x plus 2. And on the right, I'm left with 10 squared. So I'm going to go ahead and work all this out so that I can solve and get an answer. So x times x is x squared. X times 2 is 2x. Negative 2 times x is negative 2x. And negative 2 times 2 is negative 4. Notice my middle terms are opposites, so those combine to 0. And that's going to be equal to 100, which is what I get when I square 10. So I have x squared minus 4 is equal to 100. And then I want to move my 4 to the other side by adding. So I get x squared equals 104. Now this is probably not a perfect square, but it's okay because they told me I could round to 2 decimal places. So I'm going to go ahead and take the square root to get rid of my square. Don't forget your plus or minus when you take the square root. So I'm going to get x is equal to, when I take the square root of 104, it gives me 10.198 and some more stuff, which I'm going to round to the nearest hundredth, which is the second decimal place. Notice there's an 8 behind it. That 8's going to bump this 9 up to a 10, which is going to bump this 1 up to a 2. So I end up with x is equal to plus or minus 10.2. Because this is a log problem, we do have to check our inside numbers. Okay, so we're going to check x minus 2, and we're going to check x plus 2 with our two answers. We have x is equal to 10.2 and x is equal to negative 10.2. So the positive 10.2, when I subtract 2, still going to be positive, and 10.2 plus 2 is still going to be positive. So we know that one checks out. When I do negative 10.2 and I subtract 2, that's going to be negative. So that's not going to work, and actually the second one's not going to work as well. So on this one, we just have one answer. Okay. All right, let me look at one more, and then I'll let y'all try some. All right, so we have log base 4 of x minus 3 plus log base 4 of 2 equals 3. Notice, not every term has a log. If not every term has a log, then we're not going to be able to drop logs. Okay, I keep emphasizing that. Don't drop your logs unless every single one has a log. Okay, so we're going to go ahead and condense these so that we have one log term on the right-hand side, or sorry, the left-hand side. So we have log base 4 of x minus 3. Now, because it's an addition, it condenses into multiplication. So x minus 3 times 2 equals 3. Because this is log base 4, to get rid of log base 4, we're going to use exponential base 4 so that those will cancel on the left-hand side. So I have x minus 3 times 2 is equal to 4 cubed. Okay. I'm going to go ahead and distribute this 2, so I get 2x minus 6 is equal to 4 cubed. 4 times 4 is 16, times another 4 is 64. And then I'm going to move my 6 over by adding 6 to both sides. So I end up with 2x is equal to 70, and then divide off that 2, which gives me x is equal to 35. Again, we're dealing with logs. So if our unknowns are inside the logs, we need to make sure we check our inside numbers to make sure that they're not 0 and they're not negative. So we're checking x equals 35. 35 minus 3 is going to be positive, and the 2 is always going to be positive because it's just a whole number. All right, so x equals 35. All right, so I'm going to go ahead and give y'all a minute to pause the video and try to work through 1, 2, and 3 on the next couple pages. And then whenever you're ready, go ahead and play the video again and we'll go over it. All right, so for this first practice problem, we need to condense first. Because it's an addition, it condenses into multiplication. Now, once we have our multiplication, now we can get rid of our log. This is log base 10, so we use exponential base 10 to get rid of it. Make sure you're doing it on both sides. On the left, it cancels, so you're left with just x minus 3 times x plus 3. And on the right, you have 10 to the 4th, which is 10,000. Okay, we're going to distribute out the left-hand side, which will simplify down to just x squared minus 9 is equal to 10,000. And then I'm going to move my 9 over because I can solve this by just taking the square root since I don't have an x term. Now this is not a perfect square, so we want to go ahead and get it as a decimal so that we can round it to the nearest hundredth. When I do plus or minus the square root of 10,009, I get 100.4 and negative 100.4. I need to check them in my log inside values. And because the first one doesn't check out, I only have one solution, which is the positive 100.04. Okay, let's look at the second one. Second one, same idea. I need to go ahead and condense my terms. Again, I have addition. Addition condenses into multiplication. So I'm going to write both my inside numbers and just one log term being multiplied. And then I can get rid of my log base 2 by using the exponential base 2 on both sides. On the left, it will cancel out that log base 2. On the right, I'm just going to be left with 2 cubed, which is 8. Once I distribute out the left-hand side, I get x squared minus 7x. Now, that tells me I'm going to have to factor. So I'm going to move this 8 to the other side by subtracting and then set up my sum product chart. I need something that combines to negative 7, that multiplies to negative 8, which would be negative 8 and positive 1. So those are my factors since my leading coefficient is 1. So I have x minus 8 and x plus 1. And when I solve them, that gives me positive 8 and negative 1. Make sure you check them in your inside values. Negative 1 does not check out. Positive 8 works. So that's our only solution. Okay. Let's look at the third and final one. All right. On this one now, this is tricky. This probably isn't something I would put on a test, but I wanted to go ahead and give you something a little bit different. So on this one, we're actually solving for this I value. Okay. To get this I by itself, we first need to get the log term by itself. So I'm going to divide off 10 on both sides. When I divide by 10 on both sides, that leaves me with just 3 on the left and my log term on the right. Now, I only want the I, right? If I only want the I don't need that piece that's on the bottom. So a good way to get rid of this piece on the bottom is actually to expand this, because since I have a division, I know that expands into a subtraction. So I'm going to write this out as log I minus log 10 to the negative 12. And then because log is just a regular old log base 10, log base 10 and 10 are going to cancel. So log base 10 and 10 cancel, leaving me with just this negative 12 in the exponent. The negative 12 in the exponent and the negative that was already there in front of that turn that into a positive 12, which then I can subtract to the other side to combine with the 3, which gives me negative 9. Okay. Now, at this point, I still need to get rid of this log. This is still log base 10, so I'm going to use exponential base 10 on both sides. So that's what I did up here. Okay. That way, my log base 10 and my exponential base 10 cancel. And on the right-hand side, I just get 10 to the negative 9. Now, rule of thumb is if your exponent is negative 5 or smaller, or positive 5 or bigger, we go ahead and multiply it out. I mean, we don't multiply it out. Okay? If we're going to get something that gives us a humongous number or something that gives us a teeny tiny number, then we don't multiply it out. So if your exponent is between negative 5 and 5, multiply it out. If it's smaller or bigger than that, you can just leave it as is. So on this one, I would be fine with you leaving it as 10 to the negative 9th. Okay, you don't have to multiply it out and get this huge decimal, but I went ahead and put it there in case anybody didn't work it out that way. Okay, all right, so that is the end of 4.4. So you should now be able to complete all assignments corresponding to 4.4. If you have questions, be sure to ask because I'm here to help.